Hi, everyone. Welcome back to the webinar. Today, we're very pleased to have Victor Reis from University of Washington. Victor is actually a graduate student at the computer science at University of Washington, student of Thomas Rothwell. Some of you might know him. And he's speaking on an elementary exposition of Pisier inequality. Victor?
Hi, thanks for the introduction, Benjamin. So this is something that came out of some lecture notes that my advisor, Thomas, was teaching. And then Anup and I, we both had this question about the Pisier's inequality that it came off to us as a very complicated proof in his lecture notes. And we really wanted to understand it a little better. So we independently thought about it for some time, and then we both discovered that we were both thinking about it. And then we got together with some other people and just figured out a simpler way to do it. So let's start with a simple motivation. Let's see. Yeah, so there's an old theorem of John, I think it's 1948, that says basically for any convex body you have in m dimensions, you can always put a ball inside it, and a ball outside it with like the rate of the ratio of the radii is m, where m is the dimension. And you can see that this is tight. For example, this regular simplex, the incircle and the circumcircle have a ratio of m. In this case, for the plane, it's a ratio of 2. And that's kind of not very satisfying because there's still like this huge factor of m between the incircle and the circumcircle. And in some circumstances, we might want to do better, while we won't have this necessary like containment, but we might want to do better like an average in some sense. And you can see that, for example, here, if you only care about volume, then you could actually approximate this simplex, this regular simplex, by a square root m ball. Of course, it won't be contained in or out, but you can see that it's neither too close to the incircle nor to the circumcircle. So one way we can measure another property is by this notion of the mean width. So we can imagine like measuring how pointy the body is. And basically we average over all directions in the unit circle. And we look at the maximum slab that is that contains the body. And you can see that for the simplex, since it has these 3 vertices, it's going to be like a little bit bigger. And actually it's by a factor of square root log m on average. I'm hiding constant whenever I write these equals. Let's see what's before. Yeah, so the dimension of k is m. Yeah, I'm always assuming that the bodies here are full dimensional. Yeah, so hi.
It looks like you subtract the same thing out of itself. What will
you? Yeah, sorry. Here should be a min. It's maximum
okay.
minus the minimum. Yeah, I didn't notice that. Okay. Yeah, so it's like the maximum inner product minus the least one. So in the case of like a symmetric convex body, you can just have like an absolute value, but here in general, if you don't want it to be symmetric, you just take the maximum minus the minimum. Okay. Yeah, so here, at least in this example, we can do better in the sense that if we rescale this body to have the volume 1, then we only pay like a square root log, at least in terms of mean width, when we compare it to a unit ball. So that's like much better than the m factor we had before for the containment. And we can ask ourselves whether this always works, right? And actually there's a theorem of, yeah, so this is called, wait, let me see how to skip slides. Yeah, okay. So there's this theorem of Urysohn. It's a very old theorem that basically says if the volume is 1, so actually this should be a lower bound. So the mean width is always at least square root m. And if you can imagine the ball, it's actually tight. And the question here is, what about the other direction? So there's this theorem of Lewis, Figel, Tom Zach, Jagerman that shows that basically that simplex is almost tight up to a square root log factor. So basically you can always rescale this body K such that the mean width is at most square root m times the log of m plus 1. And it's actually still an open problem to improve this by another factor of square root log, which would be tight for the simplex. And I should mention that the original Urysohn's inequality is a much simpler argument than this reverse inequality. And here we're going to look at one of the main tools used in the proof of this theorem. So while we will not prove the entire theorem, we will see this Pisier's inequality, which carries most of the weight. Okay. So just a quick recap of Fourier analysis. Everyone learned this in kindergarten, but can just look at it one more time. There's every function can be written as a Fourier expansion. If you have a hypercube and you map it into the real numbers, you can always write it this way. And for this talk, we're going to write this Rademacher projection, and we write it as the linear term of f. It's just to take the linear coefficients and we add them up together. So basically we forget about all the higher order terms. And here we can notice that the L2 norm basically of the linear term is always upper bounded by the L2 norm of the actual function, because we can imagine you're just dropping the higher order terms. So we have this inequality. And actually we can write everything we have in this slide in terms also of vectors. So if we just replace everything by vector valued functions, basically nothing changes. Okay. So the question of Pisier is basically, how do we generalize this inequality we have for the L2 norm for arbitrary norms? So here, the proof here is very specific to the L2 norm, because when you take this average and we square it, we can basically cancel out the inner products and everything works nicely. But in general, this proof doesn't work for arbitrary norms. And the question is, how well can we do in general? And the theorem of Pisier is that basically you can pay a log of m factor, and this always works. So basically for any norm you have in Rm, if you sample this plus or minus 1 vector in dimensions, and we apply any function, vector valued function, then basically the L2 norm, the L2 norm in terms of this other norm of this function will always be upper bounded by this log factor of the original function. And our proof here actually shows a log of m plus a constant. So it's this factor of c is really not a big deal. I'm not going to show this in the slides, but if you just look carefully at the proof, you can figure out this stronger version. And there's a log m lower bound for this problem due to Bourgain. His proof uses some probabilistic techniques, so he doesn't actually give an explicit function. And in this argument, we also can find an explicit lower bound of log m over log m. And I should mention, like, the reason why we did this work is because the original proof of Pisier's inequality, due to Pisier, it used some complex analysis. It's just quite complicated to read. It's also written in French. So none of us really understood it very well. There's a simpler proof due to Bourgain and Millman that does not use complex analysis, but it still uses a bunch of non-constructive hammers, non-constructive heavy machinery, such as the Hung-Banach theorem and Reis representation. So it was still it seemed to be just a little too much for this problem. And there's a simpler way to do it that I'll show you now that avoids the use of these heavy machinery. Okay. So we're going to need to have some properties of this convolution. And basically the convolution is defined as you have two functions. One is vector valued, and other is just real valued. And we can average over all inputs in plus or minus 1. And we basically mix the inputs in this way. And a nice thing about this convolution is that it preserves the Fourier coefficients up to multiplication like this. So in particular, if we want to write the Rademacher projection, which is that linear term, we can just take a convolution. So for this function L, which I'll fix throughout the talk, we can write for any function, this linear term is just f convoluted with this linear function. And another fact that we use about the convolution is an inequality here, which basically follows from the Cauchy-Schwarz and the convexity of the norm. And I won't prove it, but you can believe me, it's not that complicated. Okay. So let's look at the high level idea of the proof. So the idea is that we're going to write this linear term as a sum of two terms. Yeah, so this is the proof of this fact. And the idea is we're going to write this linear term as a sum of two terms, P, which I denote as like a proxy for the linear term, and R, which is sort of like a remainder. And then we can use the triangle inequality for this L2. And this triangle inequality, you can also prove it directly using Cauchy-Schwarz. It takes a little bit of work, but it's not that bad. And the idea here is that we're going to have to bound these two different terms using two different techniques. So the first term, we use the previous fact from the previous slide. And we can just bound it using this L1 estimate for this proxy. And notice that in the right side, we already have the term we wanted in the Pisier's inequality. So that's good. But for the other term, we're going to have to use something different. And there's an argument using John's theorem that shows if you pay a square root m factor, then you only need to pay the L infinity, sort of like the L infinity of the Fourier coefficients of the remainder. And I won't prove this inequality either, but you can believe me, it's just to apply John's theorem that gives you a linear function that kind of approximates this norm with the L2 norm up to a factor of square root m. And that's where the square root m is coming from. And you can see that the convolution works nicely with linear terms and all of that. So, and notice here you also have this term which comes from Pisier's inequality, this f of x squared. So basically all we need to do now is to control the sum of these colored terms. Yeah, so basically, if we want to control the sum, so notice that we're gonna have to do some work at least. For example, if we just take r equals 0, and I guess like if m equals n, and we can just take the function to map to Rn as well, for example, then we actually pay a factor of square root m here, right? Because the expected distance of a random walk to the origin is around square root m. So this first term would be square root m. So we're gonna have to do at least something here to get this log factor improvement. Yeah, so here's an idea we can do is we can try setting for some real number t. We can say that this proxy is going to be something like this. And this is nice in a sense because it's kind of approximating the linear term, because for the linear term, you only have like a t. And for the higher order terms, you have this t to the power of the side of the set, which goes to 0 for higher order terms. So that's almost getting there. For example, for a large set, we can bound this nicely. But the issue is that for the small sets, it doesn't work too well. For example, we would need something like this, something like the first power is around 1 and the other powers are very small. And that doesn't seem to be feasible because there's no real t that satisfies these equations, or these approximate equations, I should say. So this doesn't seem to work, but there's a workaround to this, is that we can take an average over many t's. And so how is this going to work? We can have some kind of measure over the set, and we can integrate this example, and then basically we have a lot more freedom now, because this measure, like, we can take basically any set of weights we want across this -half to half interval. And we still have the same bound for large sets because we're just averaging them. But we still need to have at least a few properties here. And we're gonna choose some odd integer L for the rest of the talk. That later we're going to take it to be around 1/2 of log m. And we're gonna want to construct this function, this measure, such that the first power, when you integrate it, you get a 1, which nicely approximates the linear term. And all the other small powers, we're gonna set it to 0. I mean, for our purposes, we could have set it to like a small number, but actually you can just take it exactly to 0 here. And another thing we're going to want to make sure is that the L1 norm, which is kind of corresponding to this red term here, we also want it to be upper bounded by this L, which is like a logarithmic in M. And basically, if we can find this function mu, then we are done. However, the main issue here is how to find this function mu. And what Bourgain and Millman did in their paper, they did an existence proof for this function using some heavy machinery, like they used Bernstein's lemma and Haber-Banach theorem and Reis representation for infinite dimensional vector spaces, which seems like a lot for this simple problem. So that's why we wanted to understand this inequality in the first place. Okay, so how did we actually construct this P? So what we did was, actually, instead of powers of t, we reparameterize and we take powers of sine, which ends up being equivalent, but this makes it easier for us. And what we find is that we can construct this finitely supported distribution for which the powers of sine will match nicely the linear term. So basically, for k equals 1, you get a 1, and for other small powers, you get 0. And notice that while the Bourgain and Millman had like a continuous distribution, here's just a discrete one. And actually, we do not know how to construct it for like a continuous setting yet. Kind of like the finiteness of the distribution here is really fundamental to our construction. So we have this bound of 4L here, but actually, I just wanted to point out, to give some intuition, that we cannot do any better than L for this problem, just to get you a flavor of why this is a reasonable estimate. And that is because for any such phi that satisfies the first condition of the powers, we can write this lower bound here. And the first inequality is just for the fact that the sine is bounded by 1. And the second equality here is coming from the fact that the linear term of the sine L theta is exactly L. And all the other terms don't matter because they're being killed by this condition here. So for example, like the sine of 3 theta, what is that? That's just 3 times sine of theta minus some higher power. And here only the 3 matters. Okay, so just to give you an intuition about why we have an L here. So that's, we cannot do better than L. And actually for our construction, like I checked more carefully what the exact L1 norm is, and it actually matches the L up to a 1 over L factor, additive factor, I guess. And I guess in our original paper, we only had a 4L, but if you really look more carefully, I did the computation and you get this almost tight result, which I guess is nice in and of itself, though it doesn't really matter for the rest of the proof. So what's the construction that we're using? It's going to be this funny looking function. So we just take like a sine of L theta divided by sine squared. And we have this renormalizing factor of 2L minus 1 over L. And here the distribution we're going to take is basically we go throughout the circle in powers of pi over, in factors of pi over 2L. And we exclude the 0 and the pi for basically just technical reasons. It's also related to the fact that this does not work for the whole interval. And that's because the integral, if you were to do like an integral, that would diverge. Like it's basically like the right thing you would expect, but it's like infinity in some parts. So that's why you need to have this finite distribution to avoid this issue. So here, I'm not going to give you the entire proof of this relationship. But basically, it's just coming from a couple different facts. So the first fact is that we can write this sine function as like a nice exponential. And that's like a really well-known result. Basically, you can just use the fact that e to the I theta, that's just like a cosine plus I times sine. And it's going to be very helpful for us. And we also use the fact that we have this geometric series here. So when we add up over multiples of theta, this is basically either going to be for L if A is 0, because every single term here will be 1. Okay. Or it's going to be 0, because it's basically going to cancel out over across the circle. And using these two facts, you can prove all of these equalities that I have here. And I'm not going to actually just write out the proof because it's kind of boring. For example, for k equals 0, we can see that this function phi is odd, right? So at least for that, it's easy to see that the integral, I guess the expectation should be 0 because you're canceling out the positive and negative terms. And for a larger k, we basically just do a computation. And just to be realistic here, like how did we find this function? We basically tried a bunch of them and used Wolfram Alpha many times, and this is one of them that worked. So to be honest, I don't have like a deep intuition about why this is the correct function, but at least we can do the math and it works out. And okay, so I have shown you I guess I haven't shown you, but I have told you that it works for the powers, but I still haven't given you the L1 estimate. So the L1 estimate we need to do is we need to bound this absolute value here. And the way we do it in the paper is we basically just take this numerator of sine of L theta and replace it by 1, because it's always upper bounded by 1. And we can argue that this is bounded by 4L, because we can always just lower bound the sine squared by just a linear term, and it works out. And as I mentioned yesterday, I did some more careful math, and you can actually just have a closed formula for this L1 norm. And it's basically coming from the fact that the sign in the numerator is always going to be either 1 or 0, depending on whether j is odd or even. So for odd j, this numerator will be 1, and for even, it will be 0. So actually, there's a nice trigonometric identity that allows us to compute the L1 norm exactly. Okay. So using this function phi, we can actually construct this linear proxy that I mentioned before. And here I still have this 8, which coming from the 4. So these constants are, I'm just being lenient with them because that's what we had in the paper. So where is this coming from? So this p is just defined exactly in terms of this phi that I defined previously in the previous slide. So it's basically just doing this average over many values that I alluded to in the intuition slide. And if you take this average over many different values, then the linear term will be exactly what you want, and the higher order terms will be upper bounded by this 2 to the L factor, which is coming just from the fact that the sign is at most 1. And again, I won't give you the exact proof here, but you can believe me that it follows from the previous slide. And I guess the R here is just defined exactly as L minus P. I didn't write it exactly, but it just take it to be like the sum of xi minus P. Okay, so just to finish the proof of the inequality, we can take this L to be just 1/2 of this log plus some constant, if you will. And basically, we can upper bound this Rademacher projection norm by the sum of these scalar terms that I had in the previous slides. And the first one is going to be upper bounded by 8L, and the second one is going to be upper bounded by 8L over 2 to the L. And if you take L to be around log, then you get exactly this upper bound. Okay. So I guess if there are no other questions, I can move on to the construction of the lower bound. Okay, so for the lower bound of this problem, we're going to use a reduction. So recall that we want to show, basically we want to show that there exists a function and a norm for which this inequality here is basically tight. So what we want to do is we want to construct a function and a norm for which this Rademacher projection has a large norm compared to the original function. Okay, and so while Bourgain's original construction was giving a tight log m bound, it was not explicit. So we give an explicit function that achieves a log m over log m. So it's getting there, but there's this trade-off of being explicit versus getting the tight bound. So here's how this is going to work. So the idea is that we're going to have this reduction here from this problem to the lower bound. So basically suppose that we can find this function f that maps the hypercube to R. And this function f is going to be always upper bounded by a constant. And the linear terms, for each singleton, it's going to be 1 over square root n. And also the support is small. So if we can satisfy these 3 properties, I argue that that will imply a log m over log m lower bound for Pisier's inequality. So why is that the case? So if we can find this function big F, we can always define this function lower f to be basically just construct looking at the Fourier coefficients. And so this function f is going to map to Rm, which is like R of the support of the function. And I still have to tell you how to construct the norm. So the norm is just going to be like a maximum over all inputs to this kind of linear version of V. So basically here, the intuition for this is just that if we want to lower bound if you want to estimate the norm of f of x, that's just going to be the original L infinity norm of f. So for any vector x, f of little x in the norm is going to be upper bounded by the L infinity norm of big F. So that's always going to be a constant. And And the Rademacher projection part is also going to be basically n times 1 over square root n, because each of these singletons is 1 over square root n. And that is large because we have this lower bound of log m over log m in n. Basically, if you solve this third equation, you're going to have a log m over log m lower bound for n. So that's where this lower bound is coming from, this reduction. And again, I won't spell out the details, but I hope you will trust that this works. Okay, so all we need to do now is to construct this function big F that satisfies these three properties, and then we have our lower bound that we want. And I should mention that Bourgain, in his construction, he did the same thing, but he didn't have this log n factor here. So it was just 2 to the square root n. But yeah, I guess he didn't find the function explicitly. It was like a probabilistic argument. But it's actually going to be very similar to what we do. So we construct this function h, which is going to be very related to the f. And it looks a little random at first, but it's just we take this product of 1 plus I over square root n, and we take the imaginary part of that term. So it looks like, where did you come up with this? But the nice thing about this function is that we can upper bound the L infinity norm very nicely, because we can just upper bound it by the absolute value of the argument. Since it is a complex number, it's multiplicative. So like basically the absolute value is at most the absolute value of the original thing without the imaginary part. And it is always upper bounded by square root e. And also the linear term works nicely because it's just 1 over square root n. And the large terms are very small, like they're at most n to the side of the side over 2. And I guess this does not work yet, because if you recall here, we wanted the support to be small. The support only needs to be 2 to the square root n log n, I guess. And here the support is potentially 2 to the n. So what do? We sparsify. So basically we just take all the small side sets. There's going to be around n choose square root n of them. And what we need to do is we need to argue that still the L infinity norm of this function f does not change too much after you do this. Like the original age had the small infinity norm, and you can argue that, well, if you ignore the higher order terms, it's not going to matter too much. And of course, the linear term is still 1 over square root n as we needed here. And I guess is that all we needed? Yeah, so there's these three properties. The first is the L infinity is bounded by constant. The linear term is 1 over square root n, and also since it's sparsified, we've ignored the higher order terms. The support is small. And I should mention that, so Bourgain actually was the one who came up with this age of x. And in his proof, instead of just using this directly, he did some careful sampling of these xj's. So I think he set some of the xj's to be randomly plus or minus 1. And that was a way to sparsify this function age. So that gives you a probabilistic construction that attains the optimal log m lower bound. And here's just like a simpler way of attaining the same lower bound by just truncating this function. Okay, so I guess that's mostly what I had. And here are some open problems. As I mentioned before, we still don't know if this reverse Urysohn inequality holds. So that's a very interesting problem that I don't have any ideas for, but I think it's fascinating. And also, I think for LP norms, we can actually show a square root log m improved factor for Pisier's inequality. So notice that here, this the norm we had was some L infinity norm, but it was like after a linear transformation of this vector v. So basically, we're taking the inner product of v with a bunch of products, and then taking the L infinity norm. So it's not really a very well-behaved norm, but the claim is that for these nicely well-behaved norms, like LP norms, I think that there's a more general class. I think it's something like if you flip any sign of any coordinate, the norm will remain the same. So if the norm satisfies that, then it should have an improved square root log m upper bound. And the only proof I have seen of this is in Pisier's original paper, and he used a lot of complex analysis. So it's a little complicated for us computer scientists to understand what's happening there. So we thought about this for some time, and we don't know how to use these elementary strategies to get this improved bound either. And that's all I had.
Okay, thank you so much, Victor. Beautiful talk, and we can open for questions.
Ну, я без очков уже не могу, да. Дата анализа, дата architecture, я не знаю, или может это что мать.
All right, so are there any questions or comments? Well, Gilles is here, but I don't know if there are any comments. Maybe not. Okay, then. Thanks again for the talk. We appreciate that. And with that, so we can stop recording, but we can still chat after the talk.